Friends, very good morning to everyone. Now, let us discuss the synthetic strategies for the synthesis of phenol. We know that phenol is a molecule which has a phenyl group, like here, which is attached to the OH group. If I want to synthesize this phenol, the strategy what should I adopt? I have to break this OH, I'll take it off and keep it over here. Another remaining part is benzene. If I take benzene and react with OH, reaction should occur. As we know, benzene is electron rich. OH, it is in the form of sp3 hybrid form, and that's why it is also electron rich. This is electron rich, which can act as a nucleophile. Benzene is electron rich. As both are electron rich, they repel each other. As they repel each other, the reaction cannot occur. For attaching OH to phenyl group, the strategy what should I follow? I should either make oxygen electron deficient so that the electron rich benzene react with electron deficient oxygen, or another strategy is make the carbon in the phenyl group electron deficient so that OH minus can act as a nucleophile and react with benzene. The two strategies can be adopted. Now, the strategy to make the carbon in the benzene ring positive center, what should I do? I should start an electron withdrawing group to it so that the carbon to which it is attached becomes electron deficient. One of the methods to increase the positivity of the carbon is benzene diazonium chloride. In benzene diazonium chloride, the diazo group is attached to phenyl group, and this aza group nitrogen is electron deficient as it has 4 bonds in it. As this is deficient, it pulls the electrons from the carbon to which it is attached and make this electron deficient center. I take benzene diazonium chloride and treat with OH minus and heat it. This is electron rich and this is deficient. That's why reaction can occur. OH minus can attack on this positive center and it has to maintain its tetravalency. Carbon gives the electrons to nitrogen, which is electron deficient, and it gives rise to phenol with the liberation of nitrogen and HCl. This is the strategy which we follow for the synthesis of phenols. Now, how will I prepare this benzene diazonium chloride? Benzene diazonium chloride can be prepared by diazotization reaction. What is diazotization? Here, I'll take sodium nitrite and treat with HCl at 0 to 5 degrees centigrade. I'll get nitrous acid and sodium chloride. The nitrous acid which is formed is unstable. That's why we prepare this in situ. In situ preparation means whenever we do the reaction, we do it and utilize it immediately. It cannot be stored. Then I will add aniline to nitrous acid solution. The nitrous acid, nitrogen is a positive center because adjacent to it there is an electron withdrawing group oxygen which is more electronegative than nitrogen. It renders this nitrogen positive. The amino group nitrogen, it has lone pair of electrons as nitrogen is in sp3 hybrid form. The nitrogen in amino group of aniline is electron rich. The nitrogen in nitrous acid is electron deficient. Hence, unlike poles attract each other. The lone pair of electrons combines with the electron deficient nitrogen. It gives the electrons to it. Already it has three bonds and fourth bond is formed. What happens? It becomes unstable. It has to maintain its trivalency for its stability. That's why the bond between the OH and the nitrogen breaks. OH gets kicked away. What I am going to get? Nitroso-amino derivative. This nitrogen hydrogen bond breaks. This electrons moves towards nitrogen. It has to maintain its valency. The pi electrons over here moves on to the oxygen, and once these pi electrons are moved on to oxygen, oxygen becomes electron rich, and this HO minus combines with this H plus, and it gives rise to hydroxyazobenzene. The lone pair of electrons gives its electrons, forms the double bond with the nitrogen. It has to maintain its trivalency. OH gets kicked off, and I will get corresponding benzene diazonium chloride. Right. Another strategy for the synthesis of phenols is alkali fusion of sulfonates. Sulfonates is here benzene sulfonate. I'll take sodium salt of benzene sulfonate and treat with sodium hydroxide Na plus OH minus. Heat it at 300 degrees centigrade. OH minus is electron rich and this carbon is positive because sulfur is electronegative. It pulls the electrons towards itself, rendering this carbon positive. We have made the carbon in the benzene ring positive. That's why OH can react. The positivity is not very high. That's why we need to force the reaction to occur. That is, we have to increase the temperature of the reaction for the reaction to occur. That is, we have to give 300 degrees temperature. I'll get corresponding sodium phenoxide, which upon hydrolysis with H plus, I'll get corresponding phenol. The benzene sulfonates can be prepared by taking benzene and treating with sulfuric acid. I'll get corresponding benzene sulfonic acid. I treat with sodium hydroxide. I'll get corresponding sodium salt of benzene sulfonate. The starting material sodium benzene sulfonate, which is used for the preparation of phenols, we can obtain from benzene. Another method is, instead of using benzene sulfonate, there is availability of halobenzene, chlorobenzene. Chlorine is electronegative, that's why it pulls the electrons. The carbon attached to this chlorine is positive center. It is easily available in the market. I treat with sodium hydroxide at 623 degree Kelvin, and the positivity of this carbon in the benzene ring is less because chlorine is not as electronegative as in the previous case what we have seen. Thus, we need temperature and also high pressure, 300 bar pressure. Heat it, I'll get sodium phenoxide. Upon hydrolysis, I'll get corresponding phenol. This is a industrial process which is used for the preparation of phenols, where it is called as Dow's process. Here we treat with sodium hydroxide at 300 degrees centigrade and 3000 pounds per square inch pressure. I'll get corresponding phenol. In all these three strategies, we have taken a compound in which carbon in the benzene ring is electron deficient. In another strategy, we will go for the oxygen which is electron deficient. This is given by Bayer and Williger and it is named after it as Bayer-Williger oxidation. In Bayer-Williger oxidation, I'll take cumene. Cumene is nothing but isopropyl benzene. I treat with hydrogen peroxide, I'll get corresponding cumene peroxide. The cumene peroxide, it has OH in which there is lone pair of electrons. It is electron rich. I treat with acid H plus. H plus combines with OH. Protonation of the oxygen takes place to give rise to OH2 plus. The lone pair of electrons which it has, it gives to H plus, then it becomes deficient. To satisfy this positive center, the oxygen and the OH2 oxygen bond breaks over here. The electrons moves towards oxygen. When these electrons moves towards this oxygen, this moves as water molecule. This oxygen, as the electrons are taken away, this becomes electron deficient, which I represented as positive center. As this is positive, electron deficient oxygen, it is unstable. To satisfy this positive center, the bond between the carbon and the carbon of the phenyl breaks. This phenyl group takes away the electrons, and when it takes away the electrons, that becomes pH minus and pH minus and O plus. This is deficient and this electron rich. It moves towards this thing, the electron deficient oxygen. This is called as 1, 2 aryl shift. The aryl group at one position has shifted to the oxygen group which is electron deficient at 2 position. I'll get corresponding O phenyl group bonded with each other. As the electrons are taken away by the phenyl, what happens to this carbon? This carbon becomes electron deficient. To satisfy this positive center, OH minus I treat, it combines with plus carbon, I'll get OH. When I heat it, the bond between oxygen and hydrogen breaks. These electrons moves towards the carbon. It has to maintain its valency. The carbon and oxygen bond breaks over here and these electrons moves towards oxygen. That become O minus. O minus and these electrons have moved over here. This has become H plus. O minus and H plus have combined together to give rise to phenol and acetone. This is Baeyer-Villiger oxidation. This is another strategy where we make oxygen electron deficient. In other strategies, we made the carbon in phenyl electron deficient. The two strategies have been utilized for the synthesis of phenol. Next class will be dealing with the reactions of benzene. Thank you.